An interesting tool in Hamiltonian mechanics are the Poisson brackets. So you will see that they are very similar to the quantum mechanical commutators. If I have two functions that depend on position, momenta, and time, the definition of a Poisson bracket is the definition of a Poisson bracket, as you can see, is the sum over the degrees of freedom of the derivative of the first function according to the momenta and the derivative of the second function according to the positions minus the opposite. So the derivative of the second functions according to the momenta times the derivative of the first function according to the positions. At this point, the definition isn't so interesting. But the interesting thing about it is what you can use it for. In fact, if you want to know the total time derivative of a function, you can define it as df and dt is equal to the partial derivative according to time of the function plus the Poisson bracket of the Hamiltonian and the function. So if I want the function to be an integral of time, I can simply impose it to its quantity to be equal to 0. But the interesting thing is that if the function doesn't have any explicit time dependence, this becomes simplified. The expression simplifies to the Poisson bracket of the Hamiltonian and of the function must be 0. So this is a fast and easy way to understand if something is an integral of motion and to find integrals of motions. Some properties of the Poisson brackets are that if I invert the two functions inside the bracket, I simply have to change the sign. If I have two functions summed inside the Poisson bracket, I can simply split the bracket. If I have two functions multiplied inside the bracket, the expression will be in this form. The expression will be in this form. And if I want to apply the partial time derivative to a Poisson bracket, I can simply apply it to one element per time at a time. So this is a little bit of algebra of the Poisson bracket. Some other interesting operations you can do with the Poisson bracket is with the coordinates and with the momenta. So if I have two positions, Poisson bracket will always be 0. If I have two momenta, it will also be 0. If I have a momentum and a position, it will be a Kronecker delta. That, as you may know, means that it's 1 when I and k are equal and 0 in any other situation. So when they are not equal. So and the last interesting thing is the Jacobi identity. In fact, if I have this kind of nested Poisson bracket, if I have this kind of nested Poisson bracket and go through it cyclically, I will obtain 0. this isn't so interesting on a practical way, but on a theoretical one you can demonstrate quite a good amount of things.